So in this last chapter today, we will use the inverse function applied to gonometric functions. Let's start with the function sine. When no condition is given, we mean for any real x. This function is not injective, there is no inverse. Too bad. But if we restrict the domain of definition to the interval minus pi pi, minus pi half, then this function is already injective, and we can consider the inverse, which is denoted arc sine. And if we sketch the graph in more detail, our sine looks like that, including the endpoints. They do belong to the set, they do belong to the graph. Then the arc sine looks like that. And while sine is defined from minus pi half to pi half and has values between minus 1 and 1, then arc sine is defined for from minus 1 to 1, and it has values from minus pi half. So we can write the important property that the domain of definition of the function arc sine is just the closed interval from minus 1 to 1. And we can proceed in the similar way for the function cosine. It is not injective, it has no inverse. So we restrict the domain of definition to x from 0 to pi, and we get a function that has this graph and the inverse is called arc cosine. And it is again defined for x between minus 1 and 1. And the range is from 0 to pi. And the same story for tangent. In the English literature we use TAN. In the Czech literature we use TG. This is not injective, it has no inverse, so we restrict the domain of definition just to the interval from minus pi half, and this time it must be open interval. This was closed, this was closed, this is open. And for this interval, the tangent looks like that. So the arc tangent is a function with this graph. And as the graph of the original function has vertical asymptote for x is pi half, this has horizontal asymptote for y is pi half, and as there is another asymptote for x is minus pi half, this results in this asymptote in y is minus pi half. Yeah, they should cross in a single point. Well, and finally, for the function cotangent, again, this function is not injective, it has no inverse, so we restrict the domain of definition this time to x from the open interval 0 pi, which looks like that. And when we rotate this graph with respect to the diagonal, we get this graph. And as the asymptote was for 0 and pi, the graph of the inverse has asymptotes again at 0 and pi. There is one dangerous point. When you use cotangent in some software, like Mathematica by Wolfram or Wolfram Alpha web page, cotangent is defined in a different way. It is the same for positive arguments, but then it has a jump and it goes this way. So the green line, the green graph, is the graph of arc cotangent as defined, as used by Wolfram in his software products. The reason is that software by Wolfram considers numbers as complex numbers. And for complex numbers, there are reasonable arguments for this introduction, for this definition of the arc cotangent. But we will work with real numbers, and then we prefer the red line because there is no jump, it's not curved. We say the function is continuous. So red is our arc cotangent, green is the arc cotangent by Wolfram. So this completes the introductory chapter about functions and numbers, and next week we will talk about continuous functions and limits. Thank you for your attention.